All right, welcome back. Today, we're jumping into the sixth installment of Professor Olonrewaju-Lawal's fantastic lecture series on the basics of spatial epidemiology. We're going to be talking about a concept that's at the absolute heart of the field: disease clustering and spatial dependence. Let's get right into it. So, have you ever looked at a map of an outbreak and just wondered, why? Why isn't it just randomly spread out? You see, diseases almost never are. You'll always find patterns. Some neighborhoods, some communities just get hit so much harder than others. And figuring out the why behind that pattern, well, that's what this is all about. And this pattern, this tendency for things to group together, has a name: disease clustering. It's the simple but incredibly powerful idea that cases of a disease tend to clump up. Now, this isn't just some random fluke. These clusters are signals. They're like breadcrumbs leading us to the source. Maybe it's a contaminated well or a specific environmental toxin, or just the way an infection is moving from person to person. Our job is to follow those breadcrumbs. So here's our game plan for today. First, we'll tackle the most fundamental question: how do we even know if a cluster is real or just chance? Then we'll pull way back for the 30,000-foot view to see if there are any big map-wide patterns. After that, we're going to grab our magnifying glass and zoom right in to find specific hotspots. From there, we'll shift gears from just mapping known cases to mapping the hidden underlying risk. And finally, we'll peek inside the advanced statistical toolkit that brings it all together. Okay, so first things first. Let's say you see a few dots on a map all huddled together. How can you be sure you're looking at a genuine disease cluster and not just, well, a random coincidence? That's the first hurdle, right? And to get over it, we have to move beyond just looking at a map with our eyes and start using some serious statistical tools. Now, we can approach this in two main ways. First, there's global clustering. Think of this as your view from an airplane at 30,000 feet. You're looking down at the whole map and asking one big question. If there's a pattern, is there an overall tendency for cases to be near other cases? Then you have local clustering. This is where you land the plane and pull out a magnifying glass. You're no longer asking if, you're asking where. Where exactly are the hotspots? Where are the cold spots? So let's start with that 30,000-foot view. Before we go hunting for individual hotspots, we need to know if there's any smoke at all. Is there any statistical evidence the clustering is happening across our entire map? This is where global statistics come in. And two of the biggest tools in the toolbox here are Moran's I and Geary's C. Don't let the names intimidate you. The idea is pretty simple. For Moran's I, a value that gets closer to +1 tells you, yes, you've got strong clustering. High-rate areas are next to other high-rate areas. If it's near 0, everything's probably random. Geary's C is kind of the opposite. A value less than 1 points to clustering, while a value of 1 means probably random. Think of these as our first-pass diagnostic tests. So let's imagine our global test came back positive. Moran's I is high. We know there's a pattern out there somewhere. Awesome. But now what? Knowing there's a fire somewhere in the city isn't very helpful. You need the address. So now it's time to shift from asking if to asking where. It's time to zoom in. And the main toolkit for this is something called LISA, which stands for Local Indicators of Spatial Association. LISA is basically a family of statistics designed to do exactly this job: to go through your map, one little area at a time, and raise a flag on any spot that has an unusually high or even unusually low concentration of disease. These flagged spots, these are our targets for intervention. And inside this LISA toolkit, we've got different instruments for different jobs. Local Moran's I, for instance, is great at finding clusters of similar values, like a district with a high rate surrounded by other high-rate districts. The Getis-Ord G-star statistic, on the other hand, is specifically built to pinpoint those statistically significant hotspots and cold spots. And then you've got super powerful software like StatScan that can scan the whole map looking for clusters of all shapes and sizes. But here's the really, really crucial part. We're not just eyeballing this. We don't just find a hotspot and call it a day. We use rigorous statistical tests to make sure it's real. A common method is Monte Carlo randomization, where we basically tell a computer to shuffle our data 1,000 times and see how often a cluster that intense would pop up just by pure chance. Only if it's super rare do we say, okay, this is a statistically significant hotspot. This is real. Okay, so finding clusters of cases we already know about, that's huge. But in public health, sometimes we need to see the invisible. We need to understand the underlying risk across the entire map, even in places where we have no data points. This is where we make a huge leap. from looking at dots on a map to creating smooth, continuous risk surfaces. The classic starting point for this is a measure called the Standardized Morbidity Ratio, or SMR. It sounds technical, but the idea is dead simple. You just take the number of cases you actually saw in an area and divide it by the number of cases you expected to see based on its population. If the SMR is over 100, that suggests the risk there is higher than average. Easy enough, right? Well, here's the catch, and it is a big one. Raw SMRs are extremely unstable in places with small populations. Think about a tiny remote village in sub-Saharan Africa. If you get just 1 or 2 cases of a rare disease there purely by chance, its SMR could shoot through the roof, making it look like the most dangerous place on Earth. This creates a map full of statistical noise that can be totally misleading. Which, of course, leads us to the next big question. What do we do? How do we possibly filter out all that random statistical static and smooth out those shaky estimates so we can see the real, true pattern of risk underneath? The answer is it's an elegant solution. It's a concept called spatial smoothing. The idea is that you borrow strength from the neighbors. So for that tiny village with the wild, unstable risk estimate, the model looks at the risk in all the surrounding villages and uses that information to pull the estimate to a more stable, more believable level. It's all based on that fundamental idea that places near each other are more alike. And the sophisticated statistical engine that lets us do this kind of advanced smoothing is called Bayesian Hierarchical Modeling. This is really the cutting edge of disease mapping. It's the framework that ties all of these ideas, clustering, borrowing strength, separating signal from noise, all into one powerful model. Let's pop the hood on the most famous of these, the Besag-York-Mollié, or BYM model. Here's how it thinks about risk. It starts with the overall average risk for the whole map, simple enough. Then it adds what we can call the neighborly effect. This is the clustering part, the influence of being near high or low risk areas. And finally, it adds a local effect, which is basically all the random leftover noise that's specific to that one area and can't be explained by its neighbors. It brilliantly teases apart the structured pattern from the random noise. But what makes this so incredibly powerful is that we can also add other ingredients into the model. These are called covariates. So if we're mapping malaria risk, for example, we can throw in data on rainfall, on poverty levels, on how far people are from the nearest clinic. The model then estimates the spatial risk while taking all those other important factors into account. So after all this incredible statistical work, what's the grand finale? What's the payoff? Well, it means we can take data that's scattered, that's messy, that's full of noise, maybe from just a handful of health surveys conducted across an entire country, and we can transform it into this, a smooth, continuous risk map. This is a predictive surface that gives us an estimate of the risk for every single point on the map, not just where we took a sample. It fills in all the gaps, giving decision makers a clear, beautiful, and most importantly, actionable picture of where the danger really is. And believe me, this is not just some academic exercise. This is exactly how public health agencies predict where diseases like malaria are going to be most severe in sub-Saharan Africa. It lets them precisely target life-saving resources like bed nets or medicine to the exact communities that need them the most. It is literally turning complex data into life-saving action. And all of this leaves us with one final, pretty mind-blowing question. As we get more data every single day from satellites, from our phones, from electronic health records, and as these models get smarter and more powerful, just how accurately will we be able to predict the next outbreak? Can we finally make the leap from just reacting to disease clusters to actually preventing them before they even begin? That's the incredible future this field is building.